Light is an electromagnetic wave where the electric and magnetic fields are oscillating perpendicular to the direction of movement of light. Light from a source vibrates in many planes. Light vibrating in many planes is called unpolarized light. However, it is possible to make light vibrate in only one plane. Now, if we look at the light directly from the source, the vibrations seem to go up and down like this. So, this two-headed arrow can represent the vibrating plane. Light wave in a single plane is called polarized light. Now, we will pass this unpolarized light through an instrument called the polarimeter. The polarimeter has got two Polaroid filters. The first one is called a polarizer and the second one is called an analyzer. When light passes through the polarizer, the light that is passed through vibrates in only one plane. The other vibrations are either completely or partially cut off. The emerging light vibrates in only one plane and hence it is polarized light. Polarized filters have molecules arranged in a specific order that allows a light to pass through in only one plane. If the alignment of the polarizer is same as that of the analyzer, then we will see light glow through the eyepiece. Now the Polaroid filter of the analyzer is rotated through an angle of 90 degrees such that the analyzer's molecules are now perpendicular to the plane of the polarized light, resulting in no vibrations passing the analyzer, and we see darkness in the eyepiece. Now, if the polarized light is passed through an optically active compound kept in the sample tube, then the plane of the polarized light rotates and hence the darkness in the eyepiece is not there anymore. Darkness only exists when the analyzer is exactly perpendicular to the plane polarized light. We rotate the analyzer till we see darkness again in the eyepiece. This occurs when the analyzer is perpendicular to the plane of the rotated light. Let's assume that the initial direction of the plane polarized light coming from the polarizer is this. In the beginning, the analyzer is kept parallel to the polarizer, and hence all the light will pass through the analyzer too. If we rotate the analyzer by an angle other than 90 degrees, some light will still pass through, but its intensity will be reduced. But if we rotate the analyzer by an angle of 90 degrees to the initial direction, then the entire light will be cut off. One of the most accurate and commonly used polarimeter is a Lorentz half-shade polarimeter. It consists of a monochromatic source S, which is placed at a focal point of a convex lens L. Just after the convex lens, there is a Nicol prism P, which acts as a polarizer. H is a half-shade device which divides the field of polarized light emerging out of the Nicol P into two halves of perpendicular plane. T is a glass tube in which optically active solution is filled. The light after passing through T is allowed to fall on the analyzer Nicol A, which can be rotated about the axis of the tube. The rotation of the analyzer can be measured with the help of a circular scale C, and this E is the eyepiece. To understand the need of a half-shade device, Let us suppose that half-shade device is not present. The position of the analyzer is so adjusted that the field of view is dark when the tube is filled with only with deionized water. The position of the analyzer is noted on a circular scale. Now the tube is filled with optically active solution and it is set in its proper position. The optically active solution rotates the plane polarization of the light emerging out of the polarizer P by some angle. So the light is transmitted by the analyzer A and the field of view of telescope becomes again bright. Now the analyzer is rotated by a finite angle so that the field of view of telescope again becomes dark. This will happen only when the analyzer is rotated by the same angle by which plane of polarization of light is rotated by optically active solution. The position of the analyzer is again noted. The difference of the two readings will give you the angle of rotation of plane polarization. A difficulty is faced in the above procedure that when the analyzer is rotated for the total darkness, then it is attained gradually and hence it is difficult to find the exact position correctly by which complete darkness is obtained. For example, if the total darkness is attained at 20 degree clockwise, then at 19.9 and 20.1, it will be difficult to tell which is more darker than the other since there is nothing to compare it with. The half-shade device consists of two semicircular halves of equal size. One half is made up of plain glass and the other is made up of quartz. Without going into too much detail as we are talking about this experiment from the point of view of chemistry, it will suffice to say that the plane polarized light coming out of the glass will remain in the same plane while that coming from the quartz will get rotated by 90 degrees. When no optically active substance is present, if the principal axis of the analyzer is parallel to that of the polarizer, the glass half becomes bright while the quartz half becomes dark. If the analyzer is rotated by 90 degrees, then the quartz half becomes bright and the glass half will be dark. The analyzer is kept exactly midway between these points where both halves will be equally bright, and this brightness will be lower than the maximum brightness of each half individually. It is easier to compare two bright semicircles rather than try to achieve complete darkness of bright circle absolutely. This is the Lorentz half-shade polarimeter. Prepare the solution of the substance whose optical activity is needed to be determined. Next, clean the polarimeter sample holder with deionized water. Next, we must calibrate the polarimeter with deionized water. To do this, we must fill the sample holder up to the top with deionized water and ensure that there are no bubbles. Next, open the hatch to place the sample holder. Close the hatch and observe through the eyepiece. To ensure calibration, make sure the two semicircular halves are of equal brightness. Make sure that the inner and outer scales have their zeros aligned. If not, align them by moving the inner scale. This implies that the machine is calibrated. Next, after discarding the deionized water, fill the sample holder with the solution of the sample. Place the sample holder in the polarimeter. As done before, adjust the dial to see the two semicircular halves with equal brightness. Now note the value of rotating using first the outer dial. The outer scale is the whole number for the observed rotation reading, and the inner scale is for the first two places of decimal reading. Look for the outer scale reading which meets up with the 0 of the lower scale reading. If it exactly meets a line, then note the value of the outer scale. If it is in between two values, then use the lower value. In this example, the whole number is 1. To know the decimal point, look at the mark on the inner scale that exactly matches a mark of the outer scale. In this example, the decimal number is 1. So in this case, the reading is 1.1. If you take the reading on the left side of the machine and the inner scale 0 is above the outer scale 0, then the rotation is negative. And if you take the reading on the right side, then it will be the other way around. Meaning if the 0 of the inner scale is below the 0 of the outer scale, it is negative reading.